Okay, let's regroup on that a little bit. Two things. Let's go back to our fluid damped oscillation. Not driven, just fluid damped. We had these possible responses. It doesn't oscillate, it just dies out. It oscillates and dies out. Or it oscillates forever in simple harmonic motion, at least ideally. So I want to put up these terms here for this and summarize what we've done a bit. We have underdamped characterized by low B, damping constant. Right? And what are we going to get there? Well, that's where we're going to get T, x of t, say we'll start it out here, exponentially decaying amplitude, so it oscillates, like that, however much. Now if you keep damping it, it's going to oscillate less. We saw that over there, so it might take a long time, right? It's going to slow it all down. You keep damping it, and you get to a place where it's called critically damped. More coefficient of fluid friction there. Okay. And so that's the case where the minimum damping, so it just stops the oscillation. In other words, you're never going to go down here. You're going to start here and you're just going to go, right? That's critically damped. And that's going to take a certain, mathematically infinite time, but a certain time, get out there. Critical. Now what if you damp it more? We call that over damped. You could imagine dampening as much as you want. It's certainly not going to go back and oscillate. In fact, it's going to take a long time, even more B. And that guy's going to take the time for over damped is going to be greater than the time for a critically damped to die out. And again, it'll do that. So those are terms to know, not a big deal, but you should be able to identify them. You know the mathematical function for x here would be a sine or cosine with an exponentially decaying amplitude. This would just be a decay, right? And then we contrast that with the good old ideal, never stopping, shouldn't be that. The slope of a sine and cosine is, right, not straight up and down. Anyway, little picky things. That's that. And then when we go back to our driven, well, when we drive this system, and I'll show you that in a second too, we get to push and pull at any frequency. We're doing it sinusoidal just to keep the math easy. So we're going to push and pull and push and pull, but sometimes we might push against the motion and that'll slow it down. Sometimes we push it with it and that'll speed it up, and sometimes and so we get less amplitude if our frequency doesn't match the natural frequency of the system. And you do that with electronics. When you tune a radio to a radio station, you're getting the frequency response maximum, so you hear it. And you can just hear that station where you tune the natural resonance of your electric circuit to the external force or the external signal from the radio station that you want. Now, ideally, you don't want to hear a little bit of the other radio stations. So I'll let you explore that if you want, but we can look at a quality factor here so that all this stuff really dies out. And then you get a nice narrow peak. So how wide that peak is is something that we use quite a bit in various types of engineering and science. So the width of that peak is something we talk about. And for a radio station, you'd be just nice, crisp, clear. That station, you don't get any fuzz from the other stations. That's that kind of idea. Okay, so resonance means, how do you get it? You match the driving frequency or the external frequency with the natural frequency of the system. That makes sense. What do you get? You get the maximum response given the friction. So you get more friction, you're still not going to get as much response, but that's the best you can do. And there's lots of examples. Here's one more example. It's kind of a cool little thing, goes back and forth like that. Now I can go like that. Look at that frequency. High frequency, high angular frequency, just multiply times 2 pi. Low period, right? Doesn't take long to go back and forth. Now I can push it and pull it any way I want. I can just, you know, sometimes I can move against it. If I go against it, I slow it down, but if I can do my own thing, if I go too fast, you think, oh, you want to get more response? No, sometimes I'm killing it, sometimes I'm pushing with it, and if I go slow, sometimes again I'll kill it, and sometimes I go with it. If I go like this, pretty crazy, right? It's really moment of inertia, right? Torque, still oscillating. Increase the mass, in this case, or increase the I, right? It's got a lower natural angular frequency that it goes, so I'm going to push at that frequency, and I can still, come on now, I can still get it going until it goes crazy. And so sometimes you want resonance, your radio station, and sometimes you don't want resonance. Things like this. They say military, they walk across an old rickety bridge that they come across. Often they'll move in step like a football team or a team that's trying to get in unison, get in sync with each other, and you walk in step because you are a team and you have to have an awareness of your other folks. But then when you hit a rickety bridge, you don't want to be in step, because if you happen to match the natural frequency of that bridge, well, that can fall apart, right? When you're walking with a cup of water, you know, if it starts sloshing back and forth, either go faster or slower, it doesn't matter, so that you go off of the natural frequency of your, because when you're hitting the natural frequency, that's going to just slosh because you're pushing with the motion all the way. And so that's resonance. So that's the case where you don't want resonance, but other cases you do want resonance. So resonance is good, or it's bad, depending on what you want it to do. How do you achieve it like this? The mathematics brings us to that bridge where you start pulling in your differential equations, etc. And that's where you are at this bridge where you're getting into upper division work, and you can pull this together. So I hope that all makes sense, and that's fun. Go resonate and push things, and we're going to get on to waves.